You all set? Good. Okay. Good afternoon, everyone. Welcome to the Galsic Colloquium. It's a pleasure to introduce Dr. Krithika Manohar. Many of the folk in the audience may well know Krithika. You may be in her class. She's teaching CMS 270 this term. So Krithika is an NSF postdoctoral researcher here at Caltech. She's working with Andrew Stewart, her collaborators, as listed on her title slide here. And her work is on data-driven learning of large-scale complex systems. She has done some work in the past, very influential in terms of optimal sensor placement and forecasting. She works on control in the context of partial and limited observations, targeting applications ranging from fluid dynamics to additive manufacturing. Also interested in interpretable machine learning and operator theoretical techniques. Krithika will join the University of Washington as an assistant professor of mechanical engineering in January of 2021. So we are very pleased that she's agreed to give a Galsic Colloquium while she's part of Caltech, and also while teaching. So thank you for making the time for this, and over to you.
Thank you, Beverly. It's my pleasure to give this Galsic seminar, and thank you for the invitation. So some of you may be taking the course I'm offering at Caltech on data-driven modeling for dynamical systems. And this talk is going to explore one part of this topic, one very small part of this extremely influential topic on data-driven prediction for partially observed multiscale systems. I'm going to be talking about specifically my postdoctoral work carried out with Dmitry Burov, Dmitry Giannakis, and Andrew Stewart over in CMS at Caltech. And so I'll just begin with a little motivation for this problem of data-driven prediction. Okay, so we will consider multiscale and possibly nonlinear dynamics that we don't have access to. However, we do have observations of this X variable. So this X variable undergoes this macroscopic timescale evolution, and it is forced by some dynamics in Y, which may or may not be nonlinear. And the two scales of evolution are separated by this timescale parameter epsilon, which indicates that the Y dynamics evolve on a timescale much faster than the X dynamics. So we will investigate data-driven prediction in the context of systems such as this one, using tools in kernel methods in machine learning and operator theoretic tools in machine learning. So the goal is that we are given partial observations of the system, equispaced in time, typically at the macroscopic time scale, because it's in general difficult in applications to resolve the time scales or the time evolution of the Y dynamics, just because of how fast they evolve. So given these, we want to predict X of tau from any initial condition X naught. The challenges with this are that the governing equations are unknown, which is typical in data-driven prediction applications. And in addition, these observations are non-Markovian, which means that given the current state of X, we don't have enough information to predict the next state of X. The law is coupled to these Y dynamics. So the challenge with prediction is that we need some sort of prediction guarantees and uncertainty estimates that kind of convey what we don't know about the observations. So what do we lose from not observing Y? So that's the question we'll try to answer over the course of this talk. And this is a very relevant setting in applications such as fluid flows and climate dynamics, where we have this example of satellite data or satellite snapshot data of sea surface temperature, which are taken every week. However, we would like to predict an observable associated with the El Nino index, which is the running mean of this band of water off the South Pacific. So, if anyone, if you can't see my cursor, please let me know. But if not, I'll continue.
Yeah, it's good, we can see it.
Okay. And the goal is now to predict the El Nino index at a future time, given a snapshot of the sea surface temperature. And the snapshot is what we will be considering as X in this example, because this sea surface temperature is part of a much larger underlying dynamical system, which we cannot hope to observe. But we assume we have enough information to get some sort of meaningful prediction of the next mean temperature of that band of water. So this is something that my collaborator, Dimitri Giannakis, has thought about a lot, and he has applied kernel methods in the context of this example. However, we will consider multi-scale systems that we have defined to be of this form, and explore how the methods that we introduce will converge, in a sense, to the true forecast. So the method we'll use is called kernel analog forecasting. So here we are given time-ordered pairs of observations and responses. So you can think of the response as one component of the observations that you want to predict, and you assume you have time-shifted values of the response variable corresponding to the time window over which you want to predict. And this you'll see is important later. So KAF, or kernel analog forecasting, predicts the response forward by a time tau, which is assumed to be an integer multiple of your sampling time interval from a given initial condition X. It has an operator theoretic interpretation in terms of the underlying dynamical system, which is why it's so useful in the context of multi-scale systems. And what it does is it constructs a special kernel and averages over this kernel applied to the response data points. So it's essentially reporting a weighted average of your training data. And this kernel is actually constructed from a set of special features, phi-j and psi-j, which I'm going to call diffusion or geometric harmonics. And these are inspired from manifold learning techniques, such as diffusion maps, but they're not quite the same features, as I'll show in a minute. That's because the kernel we'll use is normalized in a different way. And you can see this is the classical Lorentz chaotic attractor, and you can see that these features actually define these geometric harmonics over the data, and they seem to be increasing in the spatial frequency here. So this is, in some sense, providing a good basis over which to define our forecast. So it's inspired and often compared to Lorentz's method for analog forecasting, which he introduced, I believe, in the 60s. It's a very simple idea. Lorentz's method essentially reports a trajectory as the prediction, a part of the trajectory within the training data itself. And it essentially looks for the closest point in the training set to the initial condition and reports the corresponding value of the observable as your prediction. Now this has been shown to be problematic in predicting chaotic dynamical systems, such as in weather or climate, and that's because it's because they exhibit sensitivity to the initial conditions. And also this reports a forecast that is discontinuous with respect to the initial conditions. So these are some of the challenges that KAF is expected to address. So just a quick outline, I'll define the Koopman operator, which is what the kernel analog forecast essentially tries to approximate. And then describe the kernel method itself, and then consider a couple of applications in multi-scale systems. So the Koopman operator is a linear operator typically defined in a space of functions. So given an ergodic flow, S tau, in some state space, depicted here, with an invariant measure mu, the operator u tau advances square integrable observables over the state space forward by time tau. So here you can see that u tau acts on observables of state space by composing them with a flow map, hence advancing them forward in time. So that's what's shown in the top half of this figure. You map to this space of observables, and in the space of observables, the evolution, the time evolution of the observable is linear and is represented by this linear operator u tau. Now, on the bottom half of this figure is what we're trying to do. We have partial observations represented by this continuous observation map H, which map from state space to a subset of state space, these snapshots xn, and we want to construct a prediction z tau that approximates the evolution of an observable that we want to consider. So that's the basic idea here, and I'm just using these sea surface temperature snapshots as a motivation. So many of you may have heard of Koopman mode decomposition, Koopman operator machine learning methods, or dynamic mode decompositions. The main observation here is that the Koopman operator linearizes what is essentially gives you a linear representation of nonlinear dynamics. So it's irrespective of the flow map tau. S tau on the previous page. The eigenfunctions, which we'll call dynamic modes, which we can call dynamic modes, or Koopman modes, phi of u delta t satisfy this relationship. So the action of this linear operator on these eigenfunctions is just it's just a scalar multiplied by the eigenfunction. So if you can represent an observable in this basis and expand an observable in the basis of eigenfunctions, then you can represent the evolution as a Koopman operator acting on these eigenfunctions and essentially evolve it by multiplying this expansion by the coefficients lambda, by the eigenvalues of the Koopman operator, lambda j. So we're looking at this in discrete time. And the VJs are essentially the modes, which are the eigenfunctions projected onto the observables. So this is the basic idea that's been initially studied by Igor Mezic and collaborators, and there's been a lot of work on numerically approximating these eigenfunctions and eigenvalues, starting with dynamic mode decomposition, which essentially started as a signal processing technique. However, the connection to the Koopman mode has been made later. So this is a non-comprehensive list of people who have list of references on and algorithms on this that try to approximate the Koopman operator. And in particular, we will look at extended DMD, which is very similar to DMD, except it tries to find a linear approximation on that fit the observables to the time-shifted observables. So first, for EDMD, the user specifies a number of observables such as low order polynomials or other functions of your state variable in which the system is thought to behave linearly. So it very much depends on the choice of the observables, and attempts to fit this linear operator A that advances these observables forward in time, and A is essentially our approximation of the Koopman operator. And ultimately what this method gives you is an eigendecomposition of this operator in terms of phi, the matrix phi, which contains as its columns the Koopman modes, and lambda, which are the eigenvalues, and essentially tries to, you can perform a rudimentary prediction of your state or your observables by simply advancing it forward using this basis of eigenvectors of the Koopman operator, or eigenmodes, I should say. There are results of when this converges to the true eigenvalues and eigenfunctions. And namely, this happens when you have a discrete spectrum associated with your system. And this occurs when the eigenfunctions, which you don't know, lie in a finite span of the observables that you pick. So it's very much dependent on this library of observables essentially designed by the user. And it can only, for a mixed spectrum systems such as, or chaotic systems which may contain both discrete and continuous spectra, you can only hope to recover the discrete spectrum, which gives you a limited understanding of systems like these. This is just a quick background on what has been done in the field. However, I just want to point out this is extremely successful when applied to many experimental data sets and fluid dynamics data sets. So here's some examples. First, of linearization. So when can you do something like this? Here you have a very simple two-dimensional nonlinear system. And then if you have this vector of observables, if you choose this vector of observables of your state, x1, the second component x2, and x1 squared, and you write the new dynamical systems you get from the observables of this of these dynamics, you get a linear system in the y coordinates. So this essentially gives you an idea of when you can do this. When you have a simple description of your system or linearizing coordinates associated with your system. However, finding these is typically a challenge. I'll not go into this here, but there are a number of advances in this community using deep learning and kernel methods that attempt to find these observables of interest. The most common motivating example of DMD is this simple vortex shedding regime of flow behind a cylinder. And in this case, you can pull out the discrete spectrum associated with this, which are the simple harmonics in time, as shown in the middle. And the dynamic modes are these spatial modes here that evolve according to these time dynamics. And you can see that each successive mode represents higher and higher spatial temporal frequencies. So DMD and EDMD are extremely good for feature extraction from complex systems where you want to essentially explain part of the dynamics and what are the dominant periodic and quasi-periodic signals within a system, an extremely high dimensional system. So there are advanced, so when you look at more complex data sets like the sea surface temperature, you end up in order to pull out signals like the El Nino, which is a highly intermittent and chaotic signal, you end up having to do this window decomposition where you look at successively smaller temporal windows of your training data in order to be able to extract things like the El Nino mode right here off the South Pacific. And based on these feature extraction techniques, you can also tackle applications and control and extremely difficult NP-hard problems like optimal sensor placement within the flow to be able to reconstruct this flow. However, I want to point out that these spectral approximation techniques can only hope to recover maybe a subset of the spectrum underlying the dynamics. And so it's not ideal for predicting the future state, which depends on the entire spectrum, especially in chaotic systems where you have continuous and mixed spectrum. So this is just a review of what has been done for Koopman spectral approximation. Now I'm going to switch gears and describe what's been done for Koopman approximation in the context of data-driven prediction. So the basic idea of KAF is to optimize over a space of functions as opposed to optimizing the best fit linear operator that advances the training data forward in time. So, so compared to the EDMD loss function, if you look at the predictor function in KAF, it's actually a minimizer over a space of functions that minimizes the L2 norm between the predictor you construct from your observation map H to the ground truth forecast U tau F, which advances the observables forward in time. This can be interpreted as a projection of the Koopman operator acting on the observables on the subspace induced by the data and the observations. And remember, we have partial observations here. So the basic idea, remember this is a kernel method, is to construct features, these features phi from a symmetric positive kernel matrix that you construct by applying a kernel function to your data pairwise. And we'll call that operator G. And we do the eigenfunction, we do the eigendecomposition of G, where G is symmetric positive definite. So it's the composition of these two operators, K star times K. And therefore, since it is symmetric, it has a orthonormal basis of eigenvectors. And each of these are n-dimensional corresponding to your data space. Now we can project the ground truth forecast, our object of interest, onto this basis of L2 that we've constructed from our data by simply projecting U tau F onto the basis functions and expanding in those bases. And these are quantities we can approximate from the data because we have sampled L2 of mu at endpoints in a long trajectory. We assume we observed enough to approximate this measure mu. So this inner product in L2 can be approximated by taking the dot product of the vector phi j and a vector of all the observable values at your training data. So this is a little abstract, but this projection of the Koopman operator only takes values at your training data points. So because the phi j are only defined at your training data points, although it's in the infinite data limit, it approximates these eigenfunctions in L2. The kernel gives us the machinery to evaluate this predictor at arbitrary initial conditions in the space of continuous functions, curly h, induced by the kernel. This is a consequence of the Moore-Aronjan theorem, which basically states that every symmetric positive definite kernel function uniquely corresponds to a reproducing kernel Hilbert space, in which the inner product is defined by the kernel, and point evaluation of any function in this Hilbert space of continuous smooth functions is given by the kernel. And the kernel I will describe in a moment, but now I'll just, for now, discuss how we evaluate z tau. So z tau is constructed basically by extending these Fj's into the RKHS, and this is given by the kernel operator. So if we define psi j as follows, as k times phi j divided by square root of lambda j, then these phi j's are orthonormal, are a basis for the RKHS curly h. And this is a consequence of just taking the inner product of psi I and psi j and using the dual operator to map to L2, and then you can see that they are indeed orthonormal in curly h. So essentially, the machinery to evaluate this pointwise is given by evaluating the kernel across all the training data with the initial point, and interpolate the Fj, the features you get from your kernel matrix. So essentially, the psi j interpolate your basis functions at arbitrary points. This is called the Nystrom extension of this function into the space of continuous functions. So that was a little abstract, but it's a result, it's a known result from Alexander and Giannakis that this converges to the conditional expectation of the Koopman operator acting on your observable conditioned on your observations. And this occurs in the limit of infinite data and infinitely many eigenfunctions. And you will see this convergence empirically, at least in the examples that I will show. Furthermore, we will be using a specially constructed kernel that compensates for variations in the sampling density of our data, particularly when we have outliers in our data, using data-dependent parameters, delta, which is a bandwidth parameter, R, which is an estimate of your sampling density, and M, which is an estimate of your manifold dimension. And all of these can be tuned in a special way from your training data. So the kernel is essentially, if you zoom out a little bit, it's just a squared exponential or Gaussian kernel, except with this special scaling given by your bandwidth, which is dependent on the data. Finally, we do a bistochastic normalization to give a symmetric positive definite kernel. And then we don't compute the kernel matrix G explicitly. We just compute the Ks and use the SVD of K to compute our eigenvectors Fj. So here are our Fj's again, defined on the Lorentz 63 attractor. There are many advantages to this. One notable one is that the eigen decomposition, which is the most expensive step, is only computed once. However, the features and eigenfunctions, eigenvalues can be reused to predict arbitrary other observables that you have with, in your training data, such as probabilities or the conditional variance associated with the prediction. So this gives us our uncertainty estimate associated with our forecast. So instead of putting in the time-shifted values of our observable f in this inner product, we can substitute this with any observable. So if you've already computed this predictor, you can substitute the discrepancy between the predictor and the ground truth into this inner product and get an approximation for the conditional variance associated with your prediction for free, essentially. And this gives us a systematic way to predict and analyze partially observed multiscale systems, especially when the scale separation is large. Okay, so now we'll move on to the applications. Just check the time here. So recall the initial motivation that we started with, which is that we want to predict x from observations of only x, although x is governed by this larger underlying, possibly nonlinear multiscale dynamical system. We assume these systems are given in this form. And as epsilon goes to 0, the scale separation between the slow dynamics x and the fast dynamics y becomes really large. And essentially, x has different closures in terms of the x dynamics alone, depending on the form of the equation. So in this form, when g is a function of only y, and y is separated from x by almost two orders of magnitude. The y time scale is separated from the x time scales by 2 orders of magnitude here. So given by s, s equals 2 here. Then the little x dynamics behave like the stochastic process in capital X, driven by Brownian motion. And again, this is a consequence of the extreme scale separation. And this is called homogenization, this regime of scale separation. Another regime we'll look at is, before I say that, I should point out that in the homogenized regime, the conditional expectation of u tau f, given our observations x, is the conditional expectation of u tau x, which is essentially the first moment of our stochastic process. So we would expect with KAF to predict the first moment of the stochastic process for future times. The second regime we'll look at is averaging. Here we assume that that R is 0, so and by is a linear term that acts to average the y dynamics, and this term we assume if we hold the x dynamics, if we hold the x fixed and integrate over the measure of y, given that the x dynamics are fixed, and that expectation of the y dynamics, given the x dynamics are fixed, is 0, then the little x dynamics satisfy this closure model in x, where this term is approximated by a closure term in x, which is unknown. So we don't need to know this to predict using KAF, but this is a common way to do model reduction for multi-scale systems to try and approximate this closure term. And under averaging, if given that we observe x, this conditional expectation of the ground truth forecast, given the x observations, essentially satisfies a linear model, and so the expectation disappears. And we expect to track the true trajectory of the system. And just a reminder that the data come from the observation map over the state space, where you only observe the x variables, and the observable you wish to predict is the x component. So let's dissect how the KAF predictor behaves under a homogenized regime. So here you have X driven by these nonlinear dynamics and this fast term in Y, where the Y dynamics are driven by an extremely fast Lorentz 63 model. And here we take epsilon to be 0.001, so we expect that the limiting homogenized regime will hold, and it converges to a stochastic process given by this equation. So we look at a trajectory of little x. This is a simple one-dimensional system where which we can study very extensively. And you can see that it kind of looks like a variable forced by Brownian motion, a double well potential. This is the histogram of the X trajectory, and we can compare it to the invariant distribution associated with the stochastic process, and you can see that they agree very closely, oscillating between these modes at -1 and +1. Now, the KAF prediction match the moments of the stochastic process, which we compute via Monte Carlo. And in order to do that, we have to simulate 10,000 realizations of the stochastic process and take the average. However, we can simply approximate these moments by simply training KAF on a single trajectory. And we can see that the ground truth is given by this gray line here. And the forecast, the conditional mean, is given by a blue line. And you can see that it converges to the mean of the stochastic process initialized. And the initial condition that we're giving to both methods is x0 equals -1. And we also compute the conditional variance, the confidence bounds associated with the forecast. So this is a prediction of the conditional variance. And you can see that it matches the conditional the variance of the stochastic process for extremely long times, and it continues for extremely long times, despite the trajectory itself behaving extremely erratically. Another neat thing about this example is you can compare the features you get for this one-dimensional example with the true eigenfunctions of the kernel operator that we constructed, and it's known to converge to eigenfunctions of a heat operator or diffusion operator defined on the manifold. So we compute the diffusion eigenfunctions associated with the stochastic process. We can do that analytically, and you can see that there's an extremely close agreement between the features, phi j, and the diffusion eigenfunctions. And furthermore, you can see how these are analogous to diffusion harmonics on the manifold defined by your data. Okay. And depending on the initial condition you give to the method, the predictor variance adapts to different initial conditions. So this is a good confirmation that the predictor works, mainly because if you begin at x0 equals 0, you start at the mean of this measure, and you can either you're equally likely to go into this lobe of the dynamics or to the positive lobe. And that's what is reflected by the larger conditional variance prediction here. Again, this is despite not knowing the Y dynamics that are forcing the system, but you can see that it actually encapsulates the true trajectory really closely at short timescales and converges to the mean at longer timescales. Okay, so now we go to a more intuitive example where KAF is expected to track the trajectory, which is the averaging regime. So we have We generate a multiscale Lorentz 96 model, which is a network dynamical system consisting of the slow variables, 9 slow variables xk, x1 through x9, each coupled to 8 fast variables. So in total, we have an 81-dimensional state space. However, if you recall from the previous slide, we're only observing the x variables, which is 9-dimensional, a very small subset of the state space. And we know that even though this is a nonlinear equation and you do still have this averaging behavior in the y term, and you have a closure model as epsilon goes to 0 in xk. However, the closure is unknown. And here you can see phase portraits of the first 3 xk for 3 different parameter regimes governed by the scalar parameter fx. Sorry for the notation reuse. So here, as fx increases from 5 to 10, you observe increasingly complex behavior in the slow variables. And on the bottom is an overlay of the xk trajectory, x1 trajectory with the corresponding average of the yj's associated with x1. And you can see that they are driven by the yj's. However, the x1 dynamics have this extremely regular behavior that can be predicted on its own as a periodic signal without knowledge of the yj's. And then we go on to more increasingly complex cases where the xk's signal is quasi-periodic and also chaotic, corresponding to the middle row of figures. The green line in each of these is generated by a model data-driven closure, if you will, where we try to learn this closure term using another method, and then we will compare this with KAF. So the method we're going to compare it with is GPR, Gaussian process regression. We train on the pairs of data xk and the averages yk to learn the closure term bk of x. And the system is extremely well studied, and it's well known that it has this closure. So in a sense, we have access to more information than KAF using the GPR methodology. So that's why it's called a model data-driven closure. So we essentially approximate this closure term using a Gaussian process, which fits a continuous function that predicts the yk given an xk. And then we simulate the closure equation given knowledge of the model, obviously. So we simulate this equation from the same initial data that we give KAF to be able to do an apples to apples comparison. So here's a comparison of KAF versus the Gaussian process for 3 different regimes. In the periodic case, we initialize along, we choose initial conditions at the left axis. So here 3, x x1 equals -2 and x1 equals 5. And you can see that over an extremely long period of time, KAF predicts the truth, it gives an exact prediction with very little growth in the error. And it stays in phase for extremely long time. In the quasi-periodic regime, it stays in phase, and where it doesn't quite overlap the trajectory, you can see that the confidence bounds do encapsulate the true trajectory and appear to grow around the extrema of the trajectory. So this is extremely promising given that you don't know the y dynamics. In the chaotic regime, as one would expect, given that you only see this initial condition, you're able to get short-term predictability over a couple of Lyapunov timescales, and then the uncertainty grows and you quickly converge to the conditional expectation. By construction, this method converges to a constant when you have mixing dynamics, and that's why you see this damping phenomena, even though it stays in phase, and the conditional variance is able to predict the window between which the trajectory lies. And you can compare with the GP learned closure, which really seems to suffer in the periodic regime because it goes out of phase quickly, while the KAF forecast stays in phase and overlaps perfectly with the trajectory. This is because it's essentially designed to approximate the Koopman operator, which whose eigenfunctions are essentially these periodic signals. And similarly with the quasi-periodic case, where you can see that over long term, the long-term GP predicted trajectory starts to go out of phase with the truth. And in the chaotic trajectory, the GP does even comparably to KAF. However, it gives no indication of when it starts diverging from the trajectory like we do with the uncertainty predictions given by KAF. And this is just a comparison of the root mean squared error associated with those plots over roughly 5,000 different initial conditions. The dotted line is GPR, and that's what you should focus on. There are other lines, but feel free to ignore them. And the blue lines, which are the KAF trained on the XK variable. And you can see that in the periodic and quasi-periodic case, KAF does much better than the GP prediction. In the chaotic case, as you would expect, when you initialize a model at the same condition, initial condition, you have short-term predictability, but then the prediction is not viable in the long term. However, since KAF is optimal in this least square sense, in this L2 sense, it tends to stay put and converges to the mean essentially of the dynamics in the chaotic case. So one thing we haven't discussed yet is, so in the previous case, we have, even though we're only looking at observations of X, the regimes were approximately Markovian in X because of the scale separation parameter being small. If we increase the scale separation parameter, then you lose this approximate Markovianity, and the XKs no longer have a satisfy closure model in terms of the XK alone. And in this case, you can see that the KAF prediction is not able to hold for a long time, and quickly the uncertainty starts to grow, and it converges to a constant even faster. With Lorenz's method, if you recall, Lorenz's method just takes the analog of the initial condition in the training data and reports the associated trajectory as your prediction. And here you can see that it stops tracking the trajectory even faster than KAF, and worse than that, it gives no indication of when it starts to diverge from the trajectory. And this is also reflected in the root mean squared error, where you can see that even in the immediate short term, even in the immediate terms, the Lorenz's method diverges a little bit, and this is reflected in the root mean squared error. And that's because it has insufficient information and has to pick between two nearby diverging trajectories in the X variables alone. So it can be easily fooled by a nearby trajectory. So that was the last result, and I see I'm at time. So to summarize, KAF gives a systematic predictor with uncertainty estimation for even in the case of partially observed multiscale nonlinear dynamical systems. And we have explored many different regimes, including periodic, quasi-periodic, chaotic, and even stochastic signals, which are interpretable with respect to the underlying dynamical system, even though we don't observe it. Numerically, the eigen decompositions or features are only computed once, and you get a prediction of the uncertainty or your trust in your forecast, as well as other indication functions, indicator functions that help you approximate probabilities of events in your system for free without having to recompute the features. Right now, we are looking at delay embeddings, delay embedding coordinates in order to get longer term predictability for chaotic signals. And this has been shown to be successful in spectral approximation of the Koopman operator in one of Giannakis' preprints, and that's something we're looking at. Also looking at studying parametric dependencies. So when the data contains data comes from multiple trajectories coming from different parameters. And that's something that's ongoing work, and that's a huge challenge in the community that is addressing or learning dynamics coming from different parameters. And another direction is to essentially use KAF as a forward model and combine with data assimilation techniques to get an even better predictor. So that's something to look at as well. And if you have any questions, you can take a look at our preprint, which is up on archive, or email or ask any questions.
Great, thank you very much, Krithika, for that really interesting talk. I should have said at the beginning, but if anyone has a question, they can either type it into the Q&A or the chat, or they can raise their hands, and then we'll promote you so that you could ask in person if you so wish.